Hi, in this video I'll be showing you how to determine the overall structure of a molecule based on 3 different spectroscopies, and that's infrared spectroscopy, nuclear magnetic resonance spectroscopy for proton, and then nuclear magnetic resonance spectroscopy for 13 carbon. And I'll just be working through a practice problem because that's one of the things that I failed to find on YouTube when I was going through this and learning it myself, and what probably would have been helpful to see what people thought of as they were going through it and what they were looking for in each of these spectroscopies and why it was that way. So that's what this video will be, and I hope you enjoy it, and I hope it helps you in your overall organic chemistry journey. So before we begin, I just want to make it clear that each different spectroscopy, so infrared, proton, and carbon, have different signals or wave numbers for each functional group or bond, what have you. So I just want to make it clear that I won't be covering the specific signals or wave numbers that each bond has. This is kind of assuming you know that. And I mean, those can be found just by looking up like signals or wave numbers for different bonds in each of these spectroscopies. So yeah. In this first one, this is an infrared spectrum, as we see. And infrared is kind of based on, it is based on how much transmittance goes through. So on the right or left side, we have these transmittance numbers. Sorry, it's so thick. And these kind of just show how much of the wavelengths went through in the spectroscopy. So obviously something up here towards like the 90 mark, or like even these ones, kind of show no molecules present because all of the transmittance is going through, 100% of it is. Whereas down here, we kind of see more, up to 25% only transmittance happening, meaning that the 75% up here is absorbed. Same thing down here, we only see 5% of transmittance absorbed, which means that the other 95% has been absorbed in some molecule. And the analysis of these molecules and these dips and, whether they be broad or sharp signals is kind of what we analyze in infrared spectroscopy, because we're looking at what molecules are present to absorb in that shape. So the first one I'd like to draw our attention to is this one on the left. This very, very broad signal here. What causes broad signals is the presence of intermolecular forces, and the most prevalent being hydrogen bonding. So I know that this is going to be some form of hydrogen bonding. When I further analyze, I know that OH bonding in specific occurs between this 3,500 to 3,000 range. So I can draw the conclusion that this one will have my OH bond because of this broad shape and because of the fact that it's in that area where OH bonding would occur. Note that infrared spectrums only really give you functional groups. They won't give you exact bonds. So they aren't really reliable completely, which is why you need to rely on something like a 1H or 13C to give you those specific bonds. Next, we'll look at one of my favorite areas, which is this alkane, and alkyne region of the graph. So the first thing I would do when analyzing this is look at the 3,000 benchmark here. Okay, so right here. Anything on the right of the 3,000 is going to be an sp3 hybridized C bond. So I know that this is going to be a sp3. So it'll be an alkane. And then to the left of that 3,000, so I'd say right about like here, we'd see an sp2 hybridized. And then even more to the left, so kind of like over here, we'd see an sp alkyne. Because we don't really have very large signals here, I can assume that there aren't really any sp or sp2 hybridized carbons, and the only one I have is this this signal on the right of the 3,000 benchmark, which I can conclude is my sp3 carbon. Let me just erase this. And then moving on to the left, I know that this will be an arene. just because in this area in organic chemistry 1, you don't really focus on the fingerprint region because this is a lot of different bonds and functional groups that kind of overlap, so it's kind of pretty difficult to analyze, and they're not that important when looking at the overall structure of pretty simple molecules. But one that does really stand out is pretty much this first one, which I know will be an arene, just because arenes are really the only ones that occur on this 1400 to 1500 area right here. So I know that this will be my arene. And again, it's assumed that you memorized or at least know the signals or wave numbers for these molecules. So as I mentioned before, infrared spectroscopy really only gives me the functional groups. So I'll need to rely on something like a 1H NMR spectrum to give me more specific bonds. Starting from the right, I like to look at this key that's given down here to kind of determine what I have going on. So on the very right, we have this 1.4 signal. It's a doublet and has 3 hydrogens. So we can assume that this is a methyl because methyls occur at around the 1.4 signal region and because it has 3 hydrogens. So I'm just going to draw like a methyl. And remember that 1H obviously looks at protons. So I'm going to draw a little guy, a little methyl group here. And then I also note that it gives me this doublet meaning, and that just means that it has a neighbor of 1 hydrogen, because remember that neighbors are giving at like the neighbor plus 1 basis. So I'll have 1 neighbor plus 1 gives me 2, so that's a doublet. So I'll know that I have a little H neighbor here. This is not really included in that, but I will know that he's there. And yeah, so then the next one is this 2.7 broad singlet with 1 hydrogen. Now, remember what I said last time about broad signals and infrared spectrums is that there's a high chance of intermolecular forces. The reasoning for that is that there's a dispersal of energy. It's not just one sharp, narrow signal because it's not an exact energy. It's kind of dispersed because some are participating in hydrogen bonding, and so we kind of see a dispersion of that energy. Same idea here. So we know that this is going to be our OH group because again it does say that it's 1 hydrogen and an OH bond would have 1 hydrogen. And then moving down, it also says it's a singlet, so it has no neighbors, so that's just on its own. That's cool. Moving on to the next, we see a 4.8 quartet and it's 1H. Now, quartet points to the fact that it has 3 neighbors. And so I'm getting pretty excited here because that could mean that it's this hydrogen that we talked about here, because that hydrogen has 3 neighbors. And that would make sense for it to go there. The one thing that you might note is pretty weird is this 4.8 signal, which is definitely not where 1 hydrogen would fit in. Usually a 1 hydrogen bond would be around this like 0.9 and 1.7 region here. So the reasoning, what first comes to mind is that it's pretty close to something high in energy. And this OH would be pretty high in energy. So I'm going to assume that this single hydrogen is most likely attached to this OH, and that, this is the rest of the atom, the rest of the structure. Just because it's really, really high in energy, so that increase in energy from the oxygen will bring it from its typical benchmark of this area and bring it all the way to having a 4.8 signal, because it's, attached to a pretty high energy group such as a hydroxyl group. And also an easy one to recognize is this 5H multiplet signal, because there is not much else that would have 5 H's than an arene. So as we can see here, let me just draw my arene. There's a hydrogen here, a hydrogen here, hydrogen here, hydrogen here, hydrogen here. So 1, 2, 3, 4, 5. And then this 6th hydrogen will not have actually this won't even have a hydrogen because this already has 4 bonds. The 1, 2, 3, 4. So there isn't a hydrogen here, it's just these 5. So that's what I got from there. Now, I'd like to point out that this 1H now gives us fragments. So the first fragment that we had was that arene. Okay. And we knew that it was attached to something. We also knew that there was a methyl group here. These are my hydrogens. Let me just zoom in. These are my hydrogens. And that this was attached to something. We knew that there was a 1H and then there was an OH attached to it because this, remember, this hydrogen was very high in energy because of this guy. And there was also an OH group. So we know that this guy's attached to something and this guy's attached to something. So now we kind of see our structure coming together. But we're not done yet because we do need a 13C NMR just to sort of back up to make sure that we have the right idea here. So 13C NMR is obviously different signals than the proton. But what we see here is multiple signals which could point to an arene. And also this is the area where alkenes and arenes would occur in a 13C NMR. So I'm going to automatically assume that this is my little arene guy. And then over here, usually in this kind of 50-ish region, 50 to like 90, about there, we'd see singular bonds between carbons and atoms. So this is where I would probably predict a CO bond to be, which could be from our COH. And then over here, we kind of see just like the normal carbon-hydrogen bonds. So I'm going to assume that this is our methyl group here. So it kind of doesn't do a lot for us, but it does back up what we had up here in the 1H NMR. And so far, I think we can establish that the 1H NMR was the most helpful because it did give us the fragments that we needed. We also can determine the fragments here, but it's pretty obvious what our fragments are, so I'll just point there. We kind of see what the fragments are there. It's just kind of a matter of comparing the signals. Now we're identifying the major product. So I'm going to refer back to my 1H NMR page where the infrared backed us up. We do have an OH here. We do have an arene here and an sp3 hybridized carbon. So when we put it all together, right, on all 3 occasions, we knew that we had an arene. Okay, and I know that that arene is on an edge of a molecule because there was 5 hydrogens that were all the same signal. So there were no differences, meaning they were all kind of equal in terms of, what was happening where. Then we knew that this was connected to some sort of hydroxyl group, so I'm going to put that here, and that there was a hydrogen here, because remember that one 4.8 signal hydrogen that we had? And then we also had that methyl group here. And this is our finished molecule. This is what we've determined from the infrared, 1H, and 13C NMR. So I'll just recap kind of what we went over here. We knew that it was a methyl group because the infrared gave us the CSP3. So this is from the IR. And we knew that there was a methyl group from the 1H NMR. The OH was given to us by everything, actually, the IR, 1H, and 13C. This hydrogen, remember, is from when we were given the information about this group and their neighbors, we determined that they had a doublet, and that meant one neighbor. And we know that this carbon couldn't really attach itself to anything but the rest of the molecule, so it had to be attached to the molecule. And there's only one hydrogen on this connection. And then the arene, it was pretty obvious to see in all the occasions, just because arenes are one of those molecules that just kind of, they have properties that nothing else does. And yeah, so if you're having trouble with this, I would just make sure to watch more practice videos on how to do them. That really helped me learn this at first. And also very important to commit these ranges at least to memory, so you know that, okay, especially in this case of the 1H that was more it was higher in energy because of this oxygen. That would have been important to understand, okay, higher energy atoms would therefore lead hydrogens that would normally be in this range to be all the way over here. And yeah, so good luck with your organic chem endeavors. I know this was a pretty difficult topic for me when I was learning it at first, but a lot of practice helps, watching more videos helped, and I hope you get it. Yeah, thanks for watching.